Okay, thanks for Travis. I don't have to do an introduction for my talk, but I'll be talking about measurements, tracking the Hungatanga aerosol cloud using space-based observations. Most of my talk, I'll be using OMS LP measurements, but in some places I will be also using SAGE, Calypso, Tropomi. This is just the first measurements of the eruptions. OMS LP measured the bloom and the first eruption that few people talk about on January 15, which took place on the 13th. It was around 18 to 20 kilometer altitude. And OMS LP also measured the main bloom on the 16th, which took place on the 15th, between 22 and 30 kilometer. That's what you see here, which was a major big things. But soon after, we start looking in our measurements, refine the retrievals. We found out that there was also a bloom on, we saw it around 46. Well, this one closer to 40 kilometer, but we're looking at the radiances. We found that we actually saw that around 46 kilometer and closer to the 50 kilometer, which by all means were the highest OMS seen in its records. So on this slide, I'm concentrating mostly on the bloom on the upper stratosphere above 36 kilometer. And I like to talk about this because in the literature, most people assume that particles do not last there; they just evaporate. And OMS LP, I have to say, we had to modify our algorithm to track the bloom at this highest altitude, up to 44 kilometers. So OMS LP tracked the aerosol clouds in the upper stratosphere for a month, when most instruments lost track within 2 to 3 days. In 1 week, what you see here, I'm tracking the highest part of the bloom transport. In 1 week, the bloom above 40 kilometers circumnavigate the globe and remain detectable for 2 weeks. The layer at 36 kilometers took 10 days to circulate the world. And here, this figure shows the aerosol extension anomaly above 36 kilometers. And what you can see that the aerosol was detectable for almost through March, about 90 days. And you can see there was first a rapid descent that took place within few days, then a slower one that lasted for 3 months. Okay, now this is OMS observations of the main volcanic plumes. Here the stratospheric aerosol optical depth. You can see the plume was mainly confined in the tropics for the first few months, and in May there was a significant parts of the aerosol layer start moving, were transported to the South Pole, and play significant role in this year's large ozone hole, at least according to Wang et al. This might be debatable, but it definitely moved toward the South Pole. And you can also see there was a transport to the northern hemisphere that started sometimes around November. You notice here there is a slight increase. In April, we did have a Shivlush eruption that took place there that might add a little bit more into the stratospheric aerosol budget. Here it's a zonal mean profiles between 30 south and 10 north for the same period, and of the aerosol extension ratio. And you can see that the main volcanic aerosol layer was between 20 and 26 kilometers altitude and exhibited a rapid descent early on of the aerosol layer during the first few weeks, then a slower one, what you can see here, in April, and the drop in aerosol values that you see here, that mostly associated with the transport of the bloom toward the lower altitude to the southern hemisphere. Okay, so what do we know about the particle composition, size, type? We need to include other instruments because OMS cannot provide all this information. So we know that from the UV measurements that the volcanic plume was rich in SO2 but poor in ash contents. And we know from Calypso that there was a near zero depolarization ratio. This is mostly persisted almost all measurements except the first day or couple of days at the highest part, and which indicate that the bloom was mostly, when you add both, it's mostly spherical sulfate particles. We also looked at SAGE. My analysis are not as detailed as Travis, but nonetheless, we looked at marsh, and here you can see the extension coefficient. You clearly see the plume at similar altitude to what OMS saw, and you can see that the angstrom here, this is the angstrom exponent, show very smaller value, indicate larger particles. So you can also see there is a transport, as a weaker transport of that volcanic aerosol toward the northern hemisphere, and we saw that clearly in OMS, and I will show that later in marsh. So angstrom exponent was between 0.5 and 1 for the main aerosol layer. We translated that to 0.21 to 0.28, a little bit lower than what Travis did, but it wasn't as detailed as his work. But there was a larger angstrom exponent of that part that was transported to the northern hemisphere, and it was 2 to 2.4 below the peak, what you see here, onto the northern hemisphere, which translated to 0.08 and 1 microns. So what do we make of that? The larger particle size and the lower depolarization ratio of Calypso indicate that there was a coagulation of the sulfate aerosol particles and condensation on a pre-existing condition, pre-existing aerosols, and this was already speculated before in Lagrange paper, and then Zhu paper confirmed that using their model simulations. But the smaller particles that we saw in the southern hemisphere, that probably mostly caused by the separation of parts of the SO2 from the water-rich main bloom at higher altitudes, which resulted in a formation of a smaller particles. Here I'm showing a global view of the volcanic plume evolution and transport. I'm showing the OMS LP daily zonal mean plots at selected potential temperatures. We start from 600, 500, 400, all the way down to 360, which is still mostly in most places in the stratosphere, except the lower parts in the tropics. So you can clearly see from the 600 there is a cross-equatorial northward transport of the that took place at almost all levels of the plume. That was already published by Schoberl et al. We also see that transport of the bulk of that aerosol layer to the South Pole, that you almost disappear at higher altitude, took place at lower altitude, and starting from 500 and to all levels. That took place following the change of the Brewer-Dobson circulations at May, and you see that the volcanic aerosol moved inside here. It moved inside the polar vortex at 360 and 380 Kelvin in August, but it remained blocked. It didn't go inside above that. You can see that here from 400 and above. And later on, it's almost after the breakup of the vortex, most of that aerosol moved to the north, or a big part of that aerosol bloom moved toward the northern hemisphere later on. You can also see the transport of the aerosol in the northern hemisphere that started in November. That's in 450. There's a hint of it here, and then moved to the lower altitude where you see it at 400, 300, but you can see it more pronounced at 360K here. I would just like to mention that we did see a brief transport that took place in April, and that was mentioned more in my paper last year. This is just to show, and if people prefer to look at the zonal mean, although we can see it, we can have similar plots like this on a daily scale. I'm showing here a monthly, started from January all the way to until May. Not completely full May, but again, I showed the small similar features to the previous one. There was already a slight of an aerosol at high latitudes at the lower altitude. That's what you see here, but you can already see the cross-equatorial taking place here and start expanding. You do see the transport to the southern hemisphere here that start taking place in as early as February, and it's clearly here you can track it in March and April, and then the larger part of the plume start moving with the change of forward circulations in May, and you start seeing now the plume is stretched around all over the globe, and then later on, you start seeing the transport toward the northern hemisphere, and again, you see the aerosol layer below 16 kilometers inside the vortex. Then you start seeing the transport toward the northern hemisphere. That's what you see here. In December, you can even track all that movement all the way to the northern hemisphere. That was continuous. And my final slide, I thought I could not resist but show the Shivluch eruption as seen by OMS-LB on board the Sumi MPP and NOAA 21. This was exciting because it was the first eruption that our new instrument in NOAA 21 managed to see. And I have to stress that the instrument is not really fully calibrated, so this is preliminary. And you could still see some biases between OMS and Sumi MPP and NOAA 21, but nonetheless, it did detect that plume just a few hours after the eruptions. The interesting part is that we know from geostationary that the plume was moving east at higher altitude faster than the lower altitude. So there was about Sumi MPP measured the plume between 13 and 14 kilometers when NOAA 21 measured it about 15, 16, 90 minutes earlier. That's because we think it was moving faster. And both instruments measured the plume near 10 kilometers, which we think that most of that plume was there. Another thing is you could see here there's around 20 kilometers. I think there was early report said that the plume reached 20 kilometers. So, and we did see this peak propagating at different orbits, different days. Although it's a little bit difficult to say because the interference of Hungatonga. But anyway, I think this is an exciting event. And that's my talk. Thank you.